Today's lesson is on momentum and impulse. This is a physics section, and it introduces a new concept in physics that we've learned, or that we haven't learned about yet, and this is the concept of momentum. So very simply, momentum is defined as the product of an object's mass and its velocity. An easier way for us to think about it, though, is as how difficult it is to stop an object. When an object is moving, there's two things that would make it difficult to stop. The one is if the object is moving at a very high speed, even if it is a very small object, like for example a golf ball traveling at 100 meters per second is not something that's particularly easy to stop, even though it is quite small. And on the other hand, an object that is very heavy is also going to be difficult to stop, even if it's not traveling at a particularly high speed. So for example, a train that is traveling at 1 meter per second but has a mass of 40 tons is also not something you could easily stop. So the concept for momentum is fairly simple. We just say that momentum, as the definition says, is the product of an object's mass and its velocity. Important here that all sections in physics require that mass must be measured in kilograms. So a common mistake is that we give you an example, or we say this ball has a mass of 50 grams or 400 grams, and you forget to convert it into kilograms. Remember, mass must always be in kilograms, and velocity in physics must always be measured in meters per second. We prefer that you write meters per second like that for no apparent reason, so just don't do that. I don't know. Right, so that is very simply what momentum is. What you can see here is the fact that velocity is a vector. Velocity is a vector quantity, which means that it has both magnitude and direction. So you remember this from grade 10 when we taught you about velocity. It is not enough to say that this car is traveling at 10 meters per second. You have to say the car is traveling at 10 meters per second east or north or in some particular direction if you want to give the entire velocity of that object. What this means, though, is it means that because momentum is a product of a scalar and a vector, it means that momentum is a vector as well. So when we refer to the momentum of an object, we're always going to say this object has a specific momentum, 5 kilogram meters per second, and that must also have direction. The direction of the velocity will always be exactly the same as the direction of the momentum. Right? There are no fancy units for momentum. You remember when we write things in square brackets, we say it is the units for this. So the units for momentum is very simply just the units for mass, kilograms, multiplied by the units for velocity, meters per second. So momentum is measured in kilogram meters per second. Right, so that's our starting point. And from there, we can write out, as we've said, the mathematical statement for momentum. And what we realize very quickly is that this actually doesn't mean all that much. Right? We can define the momentum of an object fairly easily and say this is its momentum. But that doesn't matter to us as much as the change in momentum for an object. The reason why a change in momentum for us is important is because a change in momentum implies, in most cases, that the velocity has changed. Remember, the triangle means, or is Greek letter delta, it refers to the change. So when we're talking about change, we're talking about there's some value at the start and some value at the end. So this delta would normally mean the final velocity minus the initial velocity, or final momentum minus the initial momentum. The reason why we look at change in momentum as something that's important is because a change in momentum means that there's a change in velocity, and a change in velocity means that this object is accelerating. And when an object is accelerating, we can very quickly get ourselves back to Newton's second law, which says that in order for an object to accelerate, there must be a net force that is acting on that object. So we introduced the idea of momentum pretty much just to get to this idea of a change in momentum. So as we can see here, any change to the mass or velocity of an object will change its momentum, but we are going to, in this section, we are only going to deal with changes in the velocity of the object. right? So we're always going to deal with a car or a truck or a train or a ball or something. that speeds up or slows down. We very seldom deal with objects where the object gains or loses mass. We only get there later on. Right, so as this formula here says, starts out with change in momentum is very simply the final momentum of an object minus the initial momentum of that object, where since we have said that mass is now constant, we can write this as mass times the final velocity minus the initial velocity, or simply m delta v. Right, and when we get this far, we just do a quick recap of Newton's second law. What Newton's second law says to us is that when a non-zero net force acts on an object, the object will accelerate in the direction of that force. Acceleration is directly proportional to the force, and inversely proportional to the mass of the object. The reason why we need this recap is because we are heading towards a point where we're going to be able to talk about a change in momentum in reference to Newton's second law. Okay, and we call that Newton's second law in terms of momentum. Right, so just a reminder, Newton's second law in mechanics we always said as F net is equal to m times a, where I hope you will remember that acceleration of an object was very simply the change in that object's velocity over the change in time. That was our definition for the acceleration of an object. Now, what you should hopefully start to see here is that this looks quite similar to our change in momentum. Our change in momentum is equal to m delta v. So what we can see is that Newton's second law is very closely linked to our change in momentum. And that allows us then to write Newton's second law in terms of momentum, which very simply says the net force acting on object is equal to the rate of change of momentum. So all that I've done here between my Newton's second law expression and my change in momentum expression is I've exchanged the two like values. I've said m delta v is equal to delta p, and therefore F net is equal to delta p over delta t. Right, how we arrive at this formula is not important, it's not something that you need to know, but it is useful to understand where this comes from. Because eventually, what we want you to see is that the net force acting on an object causes the object to change its momentum, but not only that, the bigger the force, the faster the change, right? That is why whenever we have something divided by time, we say that it is the rate of change, right? When we did rates of reaction, it was the rate of reaction. In this, it is rate of change of momentum, right? So what this tells us is that when a net force acts on an object, that object will accelerate, keeping in mind here that in physics, when we talk about an acceleration, we are not only talking about speeding up, we're talking about an acceleration as a change in velocity. Right, so when we say a net force acts on an object, the object accelerates. Because it accelerates, its velocity changes. Because its velocity changes, its momentum changes. And therefore, we can simplify that to the expression F net is equal to delta P over delta T. Right, so that is sort of the basic building blocks that we base this section on. We base this section on the idea that objects have momentum because they have a velocity and a mass. The momentum is a vector quantity, and as a result, we can say that since the momentum changes as a result of a net force, we can rewrite Newton's second law in terms of momentum. Right, we can do a very simple example, and we can just demonstrate a vector diagram while doing that, where we look at the change in momentum of an object, and that's with a simple example where we say, here is a 1 kilogram ball that is traveling at 5 meters per second, and obviously, as we can see, it's traveling to the right. So initially, we can calculate our initial momentum. Pi is equal to m times vi, 1 kilogram, 5 meters per second. This object has a momentum of 5 kilogram meters per second. Remember though that it is a vector, so it is to the right. This object strikes a wall and bounces back. It bounces back at, let's say, for example, 3 meters per second. Right. Later on, when we get to work energy and power, we discuss exactly how this would happen, why would it lose energy. For now, we just say it bounces back at 3 meters per second. Obviously, there's no reason why the mass of this ball would have changed, and so we can very easily calculate our final momentum. Now, what we need to remember is that we are dealing with vector quantities. So a velocity of 5 meters per second to the right is not the same as a velocity of 3 meters per second to the left. So you need to, just like in mechanics, declare a certain direction as your positive direction. It doesn't matter which way you decided was positive, if it's your initial or your final. But what you then say is your mass, obviously unchanged as 1 kilogram. Your final velocity, however, is now negative 3 meters per second because this object is traveling in the opposite direction to its initial direction. Okay, so because I've said that's positive, this one to the left must be negative. What that then tells us is that our change in momentum is, our final momentum is 3 kilogram meters per second, and that is to the left. Right, so what we can now do is we can draw what's called a vector diagram. A vector diagram literally just has an arrow representing each momentum. So my first momentum was an arrow that represented a positive momentum of 5 kilogram meters per second. My final momentum was an arrow that points in the opposite direction because this object was traveling in the opposite direction. And from this, we can then see what our change in momentum is. Our change in momentum is always going to be from the head of the first arrow to the head of the last arrow. Right, and what we can see here is that the total difference, if you see this like a number line, is to go from 5 to minus 3. The change in momentum must be negative 8. We can back that up with our equation. The equation then tells us that our change in momentum, delta P, is equal to m delta V. Mass here we said was 1. Delta V, Vf minus Vi. Final velocity we said was minus 3 minus the initial 5, and that is then negative 8 kilogram meters per second. We try not to leave answers in the negative form, so we can rewrite this as 8 kilogram meters per second, and that is then in the negative direction, so to the left. Essentially what we're saying here is that this ball had to, in order to go from 5 meters per second to the right to 3 to the left, it had to first lose 5 kilogram meters per second to the right, and then gain 3 kilogram meters per second to the left. So its total change was then 8 kilogram meters per second. Right, before we proceed, we just need to understand something called a closed or an isolated system. Very simply, in physics, please note here there's a difference between a closed and an isolated system in physics to the closed or isolated system in chemistry. So in physics, a system on which the net external force acting on a system is 0. So this allows us to use an example of, for example, of a snooker table or a pool table as an isolated system. Not because there are no external forces, right? The internal forces on this is going to be the forces that these balls exert on each other, the forces that the person hitting the ball applies on them. The external force is the fact that gravity is always acting downward on this object, that the table is always exerting an upward force, a normal force on that object. But the reason why we can still call this an isolated system is because the force of gravity and the normal force in this case are equal, which means that the net external force is 0, which makes this an isolated system. So just a common mistake here is that when asked to define an isolated system, we often say when the external force is 0, which is wrong. That is when the net external force acting on a system is 0. Right, so once we understand that, we can look at something called the conservation of momentum. So conservation, as with conservation of energy or conservation of rhinos, it is always about making sure that everything within the system stays the same. Okay, so what we're starting to do is, as you can see, these first examples are very simple. When there's only one object, there's not really much we can do about it. So what we're going to be going into now is we're going to be looking at what happens when there are 2 or 3 objects in a system, fortunately mostly 2. And so what we can start to look at is something called the conservation of momentum, which just says the total amount of momentum in a system will always remain constant. Okay? It's very closely linked to the conservation of energy. Basically has to do with when these objects are moving around within their system, they're not going to lose energy as long as it is an isolated system. So, the statement there, very important here, the definition says that total linear momentum of a closed system remains constant. That word linear is vital, because if you just say the total momentum, you technically can be referring to angular momentum as well. Now, angular momentum is far beyond this syllabus and very complicated, but it is not always conserved, even in an isolated system. Okay? So when being asked to define the conservation of linear momentum, please be sure to specify that it is the total linear momentum in a system that remains constant. Right, and they give us this formula over here, that the initial momentum in any system is always equal to the final momentum. When we're talking about initial and final here, we are generally talking about 2 objects that are going to collide with each other. Right, so the initial is their momentum just before they collide, and their final is their momentum just after they collide with each other. So, speaking about collisions, there are 2 types of collisions that we get. There are inelastic and elastic collisions. Right, so we'll start with an example of an elastic collision. An elastic collision is an encounter in which the total kinetic energy of a system is conserved. Usually, 2 bodies remain separate before and after the collision. Now, that second part of that sentence is dangerous there, because the strict definition for an elastic collision is where kinetic energy is conserved. So if you are asked to prove or to show that it is an elastic collision, the only way that you can do that is you can calculate the initial kinetic energy, and then you calculate the final kinetic energy, and if the 2 are equal, then it's an elastic collision. Right? You cannot simply say, oh, there's 2 objects before and 2 objects after, therefore it's elastic. You can't do that, because that is not how an elastic collision is defined. Right? And then that obviously leads you to the next one, which then says that if they are not equal to each other, then it is an inelastic collision. It means energy has been lost somewhere. Right. I'm not going to spend too much time going through elastic and inelastic collisions. I'm rather going to look at the types of changes of momentum. The reason for that is that these elastic and inelastic questions sort of normally come right at the end as an afterthought, where they say, is this elastic or inelastic, and then you just answer it like that. Right. Just one last note on elastic versus inelastic is when they ask to show that this is an elastic or inelastic collision, you may not start with this formula. Because by starting with this formula, you are already assuming that it's true. Eki is equal to Ek. When you're asked to show something, what you have to do is you have to calculate Eki and then Ekf, and then if they are equal, then you say, therefore, this is elastic, or if they are not equal, therefore, this is inelastic. So please just be careful. You cannot just start by assuming that it's elastic before you even have proven it. Right. So, this gets us very briefly onto probably one of the stupidest things in the syllabus, that is impulse. Impulse is more of a concept, but we've given it a formula for some reason. Right, so essentially this starts with Newton's second law in terms of momentum. F net is equal to delta P over delta T. We've discussed this, we will do a couple of examples, but for now it starts here. Now all that they've said here for impulse is they've said you can rewrite this formula as F net delta T is equal to delta P. Right. So what's confusing here is, this is Newton's second law in terms of momentum. This over here is impulse. It's impulse, meaning that when you are asked to calculate the impulse, you write F net delta t is equal to, and then impulse is measured in the product of newtons and time, of force and time, and that is Newton seconds. Even the units don't make sense. Okay? So when you are asked for impulse, this is the formula, those are the units. You can, in the same question, be asked, calculate the change in momentum of this object. Change in momentum, and then you give exactly the same value. The difference now is that momentum is measured in kilogram meters per second. Okay? So very often, you would be asked the same question and told, you're first asked to calculate the change in momentum, and you're going to write, I found the change in momentum was -8 kilogram meters per second. And then the following question, and you'll see that this question may have been for 3 or 4 marks because there was formula substitution answer. But the following question says, calculate the impulse. And then it's only for 1 or 2 marks. And then all that you do is you say F net times delta t, that is the formula or the symbol for impulse, is equal to -8, and you change the units, Newton seconds. Alright, so those are the calculation parts of impulse, which is actually something we come across less often than the actual applications of impulse. The applications of impulse, there are 3 main ones. I'm going to write the formula down. Once again, F net delta t is equal to delta t. Right, so what this tells us is that the change in the momentum of an object is dependent on 2 things. 1, it is dependent on the force acting on an object, and 2, it is dependent on the time for which that force acts. Right, and this can be used to explain any number of things, whether you're kicking a soccer ball or hitting a golf ball. It explains why it's important to follow through. Okay? The reason here is that the force that your leg applies on a ball is pretty much the same. It should be at a maximum when you kick the ball. But if you can keep your foot in contact with the ball for a slightly longer period of time, increasing the time, even though the force remains the same, your change in momentum increases. So by following through or maintaining contact, whether it's hitting a tennis ball or a golf ball or kicking a soccer ball, by maintaining that contact for a longer period of time, the force is given more time to act, and therefore the change in momentum is going to be bigger. Right, so that is the one application for impulse, right? Where we say, we explain various things. It's the same as if you need to, actually let's stop at that example. The second type of application is airbags or arrestor beds. Okay, so I've just explained hitting, increase the time, thereby you increase the change in momentum. So I've explained the third one. The next 2 are fairly similar, airbags and arrestor beds. The difference here though is that when you, let's use the example of driving a car. When you're driving a car and you drive into a wall, the car comes to a halt. Right, you go from 100 kilometers per hour to 0 kilometers per hour. Okay, that just happens, you have no choice about it, the wall stops you. Okay, so the change in momentum in this case, I'm just going to, that's example 3. The change in momentum in the example of you driving into a wall, same as a truck driving into an arrestor bed. It's when a truck's brakes fail and they need to stop themselves, they drive into that sand, what's it called, a sand trap or arrestor bed, that essentially slows them down. So in that case, the change in momentum is set. You will go from your initial velocity to 0. That's going to happen. What you have control over though, is you have control over the time. Okay, and this is where airbags are important. An airbag doesn't stop your car from driving into a wall. What it does is it allows you to change your momentum over a longer period of time. So instead of just colliding head first with your steering wheel, you very slowly brought to a halt by your airbag. Okay, so what we're doing here is we are increasing the time. And by increasing the time for which that force acts, we require a smaller force. Okay, so there's two things here. Firstly, the difference between these two examples. In the first example, hitting or kicking a ball, the change in momentum was not set. Right? The longer you kept in contact with that object, the faster it would go. So when the change in momentum is not set, if you can increase the time, you increase the change in momentum. In the second example, the change in momentum is fixed. It cannot change. So all that you can do is you can affect the time and thereby change the force. Okay? Same reason why when a truck's brakes fail, we don't just build a wall next to the road. Okay? That would also slow the truck down if it just drove straight into the wall. But if you give the truck more time over which to slow down, a smaller force is required. Okay, so that's the difference between these two examples. When you're hitting or kicking something, you can increase the time, thereby change the change in momentum. When it's airbags or arrestor beds, because the change in momentum is fixed, you can, by increasing the time, decrease the force and hopefully save yourself or someone else. Right, so those are our applications for airbags, arrestor beds, and hitting. The last example, I suppose, for airbags would be when you're catching a cricket ball, for example. Catching a ball, the ball has to go from whatever velocity it arrives at to zero if you want to catch it successfully. Right, so the change in momentum is set, but if you just hold your hands and let the ball hit, it's in contact with your hand for a short period of time, and so it applies a very big force on your hands. Whereas if you let your hands move with the ball, you apply that force over a longer period of time, contact time increases, and therefore force decreases. Right, so those are our applications. I'm going to go back to the collisions and conservation of momentum and do one or two examples there. They are all fairly similar. They all go along these lines where we say two objects. I'm going to say we have a 2 kilogram ball and a 5 kilogram ball. The 5 kilogram ball is traveling to the left at 4 meters per second, and the 2 kilogram ball is traveling to the right at 1 meter per second. Right, so because we know this is an isolated system, we know that these two objects are going to collide with each other, and then they're going to go off in some direction. Now, what we do know here is that at the end, the 5 kilogram ball is going to be moving off at 2 meters per second. That's the only information that we're given. We are asked, calculate the final velocity of this object. We can label them A and B. Right? So, this is all based on the idea that it's an isolated system, therefore momentum is conserved. And so we start with our formula, which says, in an isolated system, the sum of the initial momentums must be equal to the sum of the final momentums. The sum of the initial momentum is the mass of ball A multiplied by the initial velocity of ball A, plus the mass of ball B multiplied by the initial velocity of ball B, and that is equal then to, again, the mass of A multiplied by the final velocity of A, plus the mass of B multiplied by the final velocity of B. Right, the biggest cause of problems here is that we forget that these are vectors, and therefore direction does matter, so you pick a direction as positive. Again, it doesn't matter which one you choose, as long as you stick to it. I'm going to choose left as my positive direction. What that means is that object A, which has a mass of 1 kilogram, is initially traveling to the right, therefore has a negative velocity. Mass of 2 kilograms. Object B has a mass of 5 kilograms, is traveling to the left at 4 meters per second. Object A, still with its mass of 2 kilograms, now has an unknown final velocity, and the mass of B still 5, and its final velocity still to the left at 2 meters per second. Right, so this is the most common place where we fall short, or where we forget that these objects have velocities, and those velocities have direction, either positive or negative. Right, from here it's fairly easy to solve. This is that 2 times the final velocity is equal to 8, and therefore our final velocity is equal to 4. And this is a velocity, so we write it as meters per second. The fact that it's positive tells us that it is in our positive direction, which in this case is to the left. That being to the left makes sense to us because, as we can see, ball B has lost a certain amount of momentum and therefore lost a certain amount of energy, which explains why ball A was capable of essentially speeding up in the other direction, because it has gained momentum from that collision. There are other examples where we either start or end with different numbers of objects. So the 2 possible examples are where we start out with 2 objects that are initially moving in the same or opposite directions. They then collide and move off in the same direction together. This is not particularly difficult, and we can actually, or we must actually start with the same formula. The difference now is that we have initially the mass of object A multiplied by the initial velocity of object A plus the mass of object B multiplied by the initial velocity of object B, and then that is because these objects are combined, we can then combine their masses, mass of A and mass of B, and they combine, and therefore will have the same final velocity. The reverse of this is also possible, that you start out with 2 objects, something happens, and then they end up as, you start out with 1 object, something happens and they separate, and in which case you would just reverse this equation.